sprinters versus the marathon runner. Although they are both running sports, the 100-meter sprint and the marathon are two completely different events. The 100-meter sprint is a brief, explosive event, while the marathon, on the other hand, is a prolonged, high-intensity endurance event. The essence of the 100-meter sprint is speed, with little oxygen breathed in during its 10-second duration, making the event almost entirely anaerobic, whereas the marathon is a primarily aerobic event completed in 2 to 2.5 hours by elite marathon runners. For the body to perform exercise for any given intensity or duration, it requires energy. Energy is provided chemically in the form of adenosine triphosphate, a high-energy phosphate stored within skeletal muscle. ATP is the only fuel that can be used directly by the working muscles for contraction. Therefore, ATP must be continually resynthesized from other sources through different metabolic pathways. The intensity and duration of the event determines the fuel and the energy system that is required to provide energy. There are three different energy systems in the body. 1. The immediate system, which is fueled by the intramuscular high-energy phosphates such as ATP and phosphocreatinine. 2. The short-term system, which is the anaerobic glycolysis or glycogenolysis or lactate system, fueled by glycogen, glucose, and the glycerol backbone of triglycerides. And thirdly, the long-term system, which is the aerobic glycolysis and oxidative phosphorylation of the macronutrients, carbohydrates, lipids, and proteins. The purpose of each of these energy systems is to regenerate ATP at sufficient rates to prevent a significant fall in the intramuscular ATP concentration. The immediate energy system. Maximal high-intensity short-duration exercise like the 100-meter sprint uses the immediate energy system. There is 4 to 5 times more phosphocreatinine in skeletal muscle than ATP, and the immediate energy system begins to resynthesize ATP anaerobically via phosphocreatinine hydrolysis as soon as the working muscles contract. The rate of phosphocreatinine hydrolysis is highest within the first 2 seconds of contraction, but it begins to decline after only a few seconds of maximal contraction due to incomplete phosphocreatinine resynthesis. At this point, continued muscle contraction must rely on the ATP made by catabolizing glucose via glycolysis. The short-term energy system. Anaerobic energy for ATP resynthesis in glycolysis can be viewed as reserve fuel activated when a person accelerates at the start of exercise, or when a person performs an all-out 100-meter sprint. Anaerobic glycolysis, like phosphocreatinine hydrolysis, is initiated at the onset of contraction of high-intensity exercise, but, unlike phosphocreatinine hydrolysis, its highest rate of reaction occurs after 5 seconds of contraction. During intense exercise, if hydrogen production exceeds its oxidation, pyruvate temporarily binds to it to create lactate. Lactate then either 1. Accumulates because its production exceeds its use, 2. Is oxidized to pyruvate, or 3. Is diffused into the blood, where it is transported to the liver and enters the Cori cycle to undergo gluconeogenesis. The long-term energy system. During prolonged exercise, like the marathon, as long as there is oxygen produced to the working muscles, ATP can be resynthesized through aerobic metabolism. During aerobic glycolysis, steady-state oxygen consumption matches energy demands, and pyruvate converts to acetyl-CoA. This acetyl-CoA then enters the Krebs cycle and subsequently the electron transport chain in the mitochondria, where electrons are transferred from NADH and FADH2 to oxygen to form water and carbon dioxide in a process called oxidative phosphorylation to regenerate ATP. While one energy system will predominate over the other, both aerobic and anaerobic energy systems are always working, regardless of intensity or type of activity. The relative contributions of each energy system are dependent upon both the exercise intensity and duration. The contribution of energy from each energy system falls along a continuum. This is known as the energy system continuum. At one extreme, during high-intensity, short-duration exercise such as a 100-meter sprint, where energy expenditure of the working muscles exceed their resting values by 120 times or more, the intramuscular high-energy phosphates supply almost all of the energy required. At the other extreme, during less intense, prolonged exercise such as a marathon, where energy expenditure of the working muscles only exceeds resting levels by 20 to 30 times, anaerobic processes are not needed, and aerobic processes provide almost all of the energy required. There are various fuels in the body that can maintain ATP resynthesis. Such fuels are intramuscular high-energy phosphates, phosphocreatinine, as well as the macronutrients, carbohydrates, lipids, and proteins. There are many different metabolic pathways that these fuels use in the regeneration of ATP. Let us look at phosphocreatinine. It is stored only in skeletal muscles in amounts 4 to 5 times that of ATP. When the demand for ATP is low, creatinine kinase catalyzes the transfer of a phosphoryl group from ATP to creatinine to make phosphocreatinine. The equation for phosphocreatinine hydrolysis is creatinine, ATP in the presence of creatinine kinase going to phosphocreatinine, releasing ADP plus PI. This reaction is reversible. Phosphocreatinine is very important for events such as a 100-meter sprint when energy is required immediately and without oxygen. So, it acts like a phosphoryl group reservoir, maintaining the supplies of ATP to cells. Without it, muscles will exhaust its ATP supply before it could be replenished by other, slower processes. Yield is 3 ATP. Carbohydrates are metabolized through glycolysis, a process that can be both anaerobic and aerobic. Carbohydrates can be anaerobically metabolized to pyruvate or lactate. The aerobic conversion allows continuations through metabolic pathways as pyruvate converts to acetyl-CoA and enters the Krebs cycle and the electron transport chain for oxidative phosphorylation. During the 100-meter sprint, anaerobic glycolysis of glucose uses 2 ATP during the reaction, thus yielding a net 2 ATP. If glycogen undergoes glycogenolysis before anaerobic glycolysis, the net yield is 3 ATP. During the marathon, a further 2 ATP is provided through substrate-level phosphorylation in the Krebs cycle, and 2 ATP molecules are resynthesized during oxidative phosphorylation, regenerating a total of 36 ATP through the aerobic metabolism of carbohydrate. Muscle glycogen is the most important fuel in the 100-meter sprint, as it is immediately available when contraction occurs. Lipid Metabolism. Lipids are stored in the body as triglycerides, mostly in adipose tissue, with some intramuscular stores, as well as in the liver and in the bloodstream. Lipids are hydrolyzed down to glycerols and 3 fatty acids in a process called lipolysis. Whilst fatty acids must undergo the aerobic process beta oxidation in order to regenerate ATP, glycerol can enter the metabolic pathways. Glycerol needs to be substrate phosphorylated by API, then followed by dehydrogenation to dihydroxyacetone phosphate, then converted to glyceraldehyde 3-phosphate, and it goes down the glycolysis to produce pyruvate. Lipids are an important energy source during long-distance events such as the marathon, as they are more energy-dense than carbohydrates. Compared to the 36 ATP regenerated by a glucose molecule, each triglyceride molecule regenerates a net 460 ATP to 441 ATP through beta oxidation, the Krebs cycle, and oxidative phosphorylation, and a further 19 ATP through the glycolysis of glycerol. Lipids are not the ideal fuel for exercise because fatty acids must be transported to skeletal muscle from adipose tissue via albumin in the blood before they can be oxidized in the metabolic pathways. However, this makes them ideal for fuel in the later stages of endurance events such as the marathon, once glycogen stores have been depleted and the marathon runner's pace has dropped to approximately 50% of their maximal capacity. Protein metabolism. Protein is stored mostly in muscle in the body and also in the liver and minutely in adipose tissue. When glycogen stores have become depleted, protein can become an important fuel, and during endurance events such as a marathon, proteins can provide up to 10% of the energy needed for ATP resynthesis. Proteins have their nitrogen removed through deamination in both the liver and skeletal muscle, leaving the amino acids to enter the metabolic pathways through several ways. Some amino acids are glucogenic and yield intermediates for gluconeogenesis such as lactate, glycerol, glucogenic amino acids like alanine and glutamine. Other amino acids are ketogenic like leucine and lysine and yield intermediates that are synthesized to triglycerol or catabolized aerobically for energy in the Krebs cycle. The total ATP regeneration by protein is dependent upon where it enters the metabolic pathways. Fuel used in the 100-meter sprint and the marathon. The 100-meter sprint. The 100-meter sprint utilizes both phosphocreatinine and the glycogen as fuel. There is enough phosphocreatinine in the leg muscles to provide half the ATP needed for the race. Glycogen therefore provides the other half of the energy required. In the 100-meter sprint, it takes 1 to 2 seconds for the rate of glycolysis to increase at the required factor of at least 1000. Thus, phosphocreatine hydrolysis contributes to the majority of ATP production during the first 2 seconds of the race, while glycolysis reaches its maximal rate. Research has shown that maximal sprinting performance is achieved through the simultaneous use of phosphocreatinine and glycogen. The marathon. During a race, the marathon runner uses approximately 75 kilograms of ATP, and as this amount cannot be stored in the body, ATP is resynthesized from different fuels. That is, from phosphocreatinine, carbohydrates, lipids, and proteins. The catabolism of these fuels provide the energy required. Based on simulated tests, elite marathon runners utilize 5 grams of glycogen per minute. Therefore, it can be calculated that the elite marathon runner would be exhausted after only 90 minutes of running if they only use carbohydrates as a fuel. Glycogen and glucose cannot be stored in amounts sufficient to entirely fuel the marathon. Thus, other fuels also contribute to ATP resynthesis. Lipid stores in the body are almost 35 times that of carbohydrate stores. They are also stored dry, whereas carbohydrates are stored wet. That is, carbohydrates store 3 grams of water for every gram of glycogen. Lipids are hydrophobic. Therefore, lipids or fats become the primary energy fuel during the marathon once carbohydrate, that is, glycogen stores, are depleted. Limitation of fuel stores and supply and fatigue. Fatigue is inevitable during high-intensity exercise. Fatigue is defined as the inability to maintain a given or expected output or force. So, an example of this is when our friend Mark became exhausted and out of breath after a few seconds of running. For him, his body could not maintain the expected output. Lactic acid production. As our bodies perform strenuous exercise, we begin to breathe faster as we attempt to shuttle more oxygen to our working muscles. The body prefers to generate most of its energy using aerobic methods, that is, using oxygen. Some circumstances, however, such as evading the historical saber-toothed tiger or lifting heavy weights, require energy production faster than our bodies can adequately deliver oxygen. In those cases, the working muscles generate energy anaerobically. This energy comes from glucose through a process called glycolysis, in which glucose is broken down or metabolized into a substance called pyruvate through a series of steps. When the body has plenty of oxygen, pyruvate is shuttled to an aerobic pathway to be further broken down for more energy. But when oxygen is limited, the body temporarily converts pyruvate to a substance called lactate. Lactate allows glucose breakdown and thus energy production to continue. The working muscle cells can continue this type of anaerobic energy production at high rates for 1 to 3 minutes, during which time lactate can accumulate to high levels. A side effect of high lactate levels is an increase in the acidity of the muscle cells, along with disruptions of other metabolites. The same metabolic pathways that permit breakdown of glucose to energy perform poorly in this acidic environment. On the surface, it seems counterproductive that a working muscle would produce something that would slow its capacity for more work. In reality, this is a natural defense mechanism for the body. It prevents permanent damage during extreme exertion by slowing the key systems needed to maintain muscle contraction. Once the body slows down, oxygen becomes available and lactate reverts to pyruvate, allowing continued aerobic metabolism and energy for the body's recovery from strenuous activity. The 100-meter sprint. During the 100-meter sprint, the greater the oxygen deficit, the greater the ATP and phosphocreatinine stores are being depleted, and the greater the accumulation of lactate. Since phosphocreatinine is limited, as mentioned before, continued muscle contraction must rely on ATP made by catabolizing glucose via glycolysis. The end product of this pathway is lactate. Lactate decreases the pH of the tissues in which it accumulates, and studies with isolated muscle preparations have shown that decreasing skeletal muscle pH either 1. Impairs muscle contraction by disrupting calcium release, or 2. Inhibits ATP resynthesis. Of course, if too much lactic acid builds up and the pH continues to drop, muscle pain sets in. The marathon. Further studies show that during endurance exercise like the marathon, fatigue is a response of the brain as a consequence of glycogen depletion in the type 1 muscle fibers. Type 1 fibers are also known as slow twitch fibers. They are red in color due to the presence of large volumes of myoglobin as well as oxygen and high numbers of mitochondria. Due to this fact, they are very resistant to fatigue and are capable of producing repeated low-level contractions by producing large amounts of ATP through an aerobic metabolic cycle. Hence the reason they are important in endurance exercises like the marathon. For this reason, the muscle containing mainly type 1 fibers are often postural muscles, such as those in the neck and spine due to their endurance capabilities. Also, athletes such as marathon runners have a high number of this type of fiber, partly through genetics and partly through training.